How could it bring somebody down if I never made a sound again? In your eyes, you've already spent my thighs, and you're rocking to the next big thing. Kissing the bride, 45 minutes aside. This was my dream, played out rocket routine. Who sucked out the feeling? Who sucked out the feeling? Where'd you go now that everybody knows that we did a couple shows out there? Look at me, I can write a melody, but I can't expect a soul to care. Kissing the bride, 45 minutes aside. This was my dream, played out rocket routine. Who sucked out the feeling? Who sucked out the feeling? Who sucked out the feeling? Who sucked out the feeling?
Hopefully that does it. But it's saying that it's working. But I've got some backups just in case we need them. In any case, we're going to continue where we left off last time. I introduced this notion of a linked list as an alternative to an array-based list. We went through an entire design and implementation of an array-based list. And we went through this iterative process, this feedback process, where we design the interface first. Then we design the tests, and then we do our implementation to see if it conforms to the tests and actually works. We're going to do the same thing here for a linked list. A linked list is different in that it's not all stored contiguously in memory. Instead, you've got a head of the list, right? And each element is stored in a node. The element could be like, say, 42, 8, 2, 7, right? And each node contains a reference to the next node. That node contains an element and a reference to the next node, the next node, the next node. How do you know that you're at the tail of this list? Well, there is no next node, that it ends up being null in Java. Or here I'm just using the Greek letter phi to indicate the end of the list, right? So every single thing that you're going to do with this, every basic operation is going to involve traversing this list. You're always going to be starting at the head and traversing to the node or nodes that you need to get to, all right? We're going to design and implement this from the ground up. My first step is going to be to take care of one single node, right? That's one single node right there, which is going to hold an element and a reference to the next node, right? So I'm going to go ahead and create a class here, and I'm going to learn from my mistake last time. I'm not going to just make this for integers. I'm going to make this parameterized for anything, right? I'm going to call it node, and I'm going to parameterize it with t. Remember that t is here type, right? So that this could be a node that holds an integer, like in this picture right here. Or it could be a node that holds a string, hello, names, or whatever, right? It can hold anything as long as you parameterize it. The two things that I need to keep track of are an element. Right? What type is that element? It's not an integer. It's not a double. It's not a string. Right? It is a t. Right? And then we also have a node, t next, which I'll call next here. Right? Now, wait a second. We're inside of this class here. Right? We're in the node class, and we're making reference to the node class. It's kind of hinting at recursion, but it is not recursion, right? It is not even what's called open recursion, where we use the this keyword, right? That is an object being able to refer to itself. This is not referring to itself. This is referring to another instance of that object. All programming languages allow you to do something like this, including C. You can define a structure within a structure, but also that structure within a structure can be an instance of the structure itself, right? So this is not that weird, okay? I'm going to immediately come up here to source and generate, say, getters and setters. First of all, let's go ahead and go with a constructor using fields. I'm not going to select the next. You can go ahead and have multiple constructors if you want. But this one is going to be able to construct a new node without having to specify a next. In other words, suppose that I want to insert a new element called x, right? Then I could create a node with x in it. Well, I need to insert it in this list somehow, right? So what's it going to be referring to? Well, who cares? Null, right? I'm going to ultimately, if I want to insert it somewhere, I'm going to reroute this one down here, and I'm going to reroute this one up here so that I can insert it where it needs to be. So it's not that useful to have a constructor that takes both of these things. If you want to, we can go ahead and put one there. But I'm going to make sure that I've got multiple constructors at least, right, with at least this one. Create a node with something in it, okay? I'm also going to want to generate getters and setters. In this case, I'm going to generate all, select all. Why? Because ultimately this list is going to be putting stuff, CRUD, right? Create, retrieve, update, and destroy. I'm going to be putting stuff in, I'm going to be taking stuff out, I'm going to be replacing stuff, in which case I want to reset the element. I want to be inserting stuff, so I want to get the next node, and then I also want to set the next node because I want to do some sort of rerouting like this, right? Okay? So I've got getters and setters everywhere already, okay? Now what I need to do is I need to define a list, right? It's not going to be my array list. Instead, it's going to be new class my linked list. And once again, I'm going to learn from my mistakes, and I'm going to immediately parameterize it so that it is a list of strings and a list of integers and a list of doubles, whatever you want. Now, what do I need to keep track of in here? If I were to keep track of every single node in this list, I'm right back at square one, right? Why aren't you just keeping track of every single element using an array, right? So what I'm going to do is I'm going to keep track of one of these things, because from the head, I can get to the next one, the next one, the next one. I can get all the way to the tail, right? And we do call this head and tail, right? All I'm going to keep track of, though, is the head for now, right? If you want to add in support to keep track of the tail later on, we can. But I'm going to make it into a private node t the head of the list, okay? Now, what would a default constructor look like here? Public my linked list. Right? And we're just going to say that this dot head is equal to, well, there's not going to be anything in there initially, right? So what was I using here to indicate that there's no next node, including nothing here at all? What should I be pointing this to? Phi, or in Java language, that's going to be null. There. Okay? Now, this feedback loop here, where I design the interface, then design the tests, and then implement the interface to see if the tests actually work. And then I go back and forth on all this. I already went through this process once with my array list. Right? So why don't we just steal that process immediately? Right? If you want a way to add something to the end of the list, all right, I'm going to want that function. I'm going to want a way to add something to an arbitrary index. I'm going to want a way to get a particular element at an index. I'm going to want a way to remove and replace an element at a particular index. Maybe a way to report what the size of the list is, et cetera, right? In other words, I want all of this stuff. But obviously, it's not going to be the same because this is a completely different way of representing data in a linked list. How can I make sure that this list and this list is not duplicated as far as the interface goes? By creating a new interface. And I'll call it just my list. Now this is a pure abstraction, a pure interface. I'm going to go ahead and cut and paste everything that I wanted. But remember that this is not going to be an actual implementation. It's going to be abstract everywhere. Right? I do not have an implementation that I know about. So I'll go ahead and get rid of all of these bodies. And what have I essentially done? I've said what a list is. I've defined what a list does, or what a list should do if you were to implement one. Right? Now let's come over back to my original array list that I stole all this from, and let's say that I implement my list interface for elements of type T. That makes my array list into a list. My linked list here will do the same. Implements my list of elements of type T. And now it's going to complain about it because you're not actually doing anything here. But let's think about this visually, all right? That I've got this interface now that says my list. Right? Now I've got subclasses. I've got a specialization here that holds stuff in an order and gives you these 4 or 5 methods, but it holds them using an array. Right? My array list. And I've also got a version that holds them in a linked list, or it will once I've got it implemented, right? There we go. Okay. Now I've put these into an inheritance hierarchy, right? And what I can do over here in my demo class is I can be more abstract. I can say my list of, say, integers, right? I'll just call it list, is equal to new array list, my array list, right? There you go. And I can add stuff, right? I've got a common interface here. I can add 42. I can add, what were the other values I had? 8, 2, and 7. 8, 2, and 7, right? But it doesn't matter that I'm using my integer array list, or my array list, excuse me. I could change this to a linked list. Did I have to change any of the code at all? So think about your current project and how you're going to go about changing it so that you're loading from a database. If you had used object-oriented programming from the beginning, right, then it would be simply just, I need to implement all these functions over here, but for databases instead of CSV files. And then over here, only this one line of code needs to change. Where I instantiate a CSV data loader, now I'll instantiate a database data loader. Right? We weren't expecting that in the first phase because we hadn't covered object-oriented programming, but it might be a good idea to go back and redesign it now. Right? Not that you have to, we're not going to double doc you or anything like that, we're not going to regrade it or anything, but that's what I would do. In fact, that's what I did. Right? I defined what a data loader was, knowing that sometimes I'm going to load from CSV files. Sometimes I'm going to load from a database. Sometimes I'm going to load from XML files. Sometimes I'm going to load from JSON files, right? I don't want to have to go and change the code every single time that I'm changing what I'm doing here. At least not a lot of the code. I just want to change one line, right? Like I would change it right here to go back to an array-based list. Right? But for now, let's just go ahead and go with my linked list. Right? Now, obviously, this is not going to work. Right? Because I have not actually implemented these methods because it's not even compiling yet. So let me go ahead and add unimplemented methods here. It auto-generated all that code for me. Awesome. Right? Now it's still not going to, I mean it is going to compile, but it's returning null for all these things. Okay? This tells me what I have to do now. And also it didn't copy the documentation because the documentation is up here in one place. Right? Okay. So let's go ahead and get rid of all this stuff that we don't need anymore. And let's focus on our implementation now, along with the tests as we go. I've already got a test here, basically. I need to verify that the list is now 42, 8, comma 8, comma 2, comma 7. Okay? So we need to be able to verify that somehow. Right? The way that I'm going to do that is I'm going to go system.out.println done testing. I'm going to use the debugger, right, at first. Okay. Now I could run this, but this function doesn't actually do anything yet. Okay. So we're on that other step where we design the interface because we already did that last week. We just stole it and put it into an inheritance hierarchy using object-oriented programming. I've already designed some ad hoc tests. I put 4 things in there. I need to make sure that those 4 things are in there now. Now let's go ahead and start implementing. Okay? So, how do I add something to the end? let's whiteboard it first, okay? Well, first of all, what's the first step? You're gonna have to create this new node with X in it, right? So 1, create the node, right? 2, I need to insert it right here where it needs to be, but can I jump immediately to this tail like I did with an array-based list? An array-based list is all based on memory, right? You can jump to the ith element immediately using indexing, right? But I can't do that here. What do I have to do? I have to start at the head, right, which is right here, and then I have to go to the next. That's not the end, so I have to go to the next. That's not the end. I have to go to the next. That is the end, because if I look forward here, dot, 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 I see that I would fall off the edge of this linked list. I want to make sure that I'm stopping right here, because all I need to do to insert it at the end is, instead of pointing it to null, I now need to make it point to this new node that I just created, okay? So let's outline that idea over here. One. Create a new node holding X. 2, traverse the list until you get to the last node, right? 3, make the last node point to the new node, right? 4, anything else? Anything else? Right? Okay. So let's go ahead and do this now. I always find it helpful to outline something, even if it's just in my head, right? If you get good enough to the point where you can do it in your head, great, right? But then I'm always interrupted, right? And this is why programmers usually are 2 screens with headphones on and everything like that, because they don't want the jackasses coming up behind them and say, hey, how was that game last Monday or whatever, right? Or if they're fortunate enough to have their own office, they shut their door. Make sure that if you've got windows, right, you make sure that they're covered up with posters or something so that they don't know you're in there. And then so that you can concentrate, because once you're in the zone, you don't want to get out the zone, right? Once you're in the zone, you are in the mindset of doing something. But if you get interrupted, unfortunately, that's a context switch. In fact, that's a computing term, right? When one program is running in an operating system and then it needs to be put to sleep or paused so that another program can take over, it's called a context switch, right? It's switching context to a different program. Humans do that too, but we're not really good about switching back and forth immediately like a computer, right? So create a new node, right? Again, if you're good enough, you can, and you're distraction free, you can probably do this in your head, but I'm going to go ahead and do it right here, right? Outline it. New node, node T, I'll just call it new node, is equal to new node of element of type T. You can elide that away, holding X, okay? I've got this new node right here now, and it's not pointing to anything, but it is holding X, whatever X is. I now need to traverse to the end to get to the last node. There aren't always going to be 4 elements there. So this process, this general process where I go from one to the next, to the next, to the next, to the next, tell me how I can achieve that. Yeah.
Go until like the second part of the node is null.
Okay. So in other words, I'm going to have to keep track of a current node. Right. Let me go ahead and highlight that in green there. Now, initially, that current node is going to start where? Right there at the head, right? Because that's the only place you can start. And then you would advance that to the next one. Advance that to the next one. Advance that to the next one. Do I advance that all the way? Careful, I've fallen off. I want to make current point to this new node down here. So I need to go until the next node of the current node is null. Right? I keep going if it's not null. What kind of a loop does that suggest to you? A while loop. Why? Because we don't know how many nodes are in there until we get to the end. Right? That means I need a node T, current node. Where do I start? At the head. While the current node dot get next, right, is not equal to null, right? then I advance the current node to the next node right next to it. Okay? Once I've broken out of this, I can make the current node is now at the last node. I can say current node dot set next to the new node, because that's what my outline tells me to do. Okay? Anything else? Do what? Yeah. All right, we'll come back to that. Let's come over here and test it. Current node is null. When did that happen? On that line, okay, fine. It happened when I tried to add 42 in there. So what was my assumption here when I outlined this? My assumption was that there are 4 elements in there already, right? Is that assumption valid as of line 31? How many elements are in there already? None. What does it actually look like? It looks like that the head is pointing to null, right? So in other words, in this one situation, right? If I want to create a new node with X in it, right? If I want to insert it at the end, what does that situation look like? I don't not make head point to null anymore. What do I make it point to? That node, right? This is what's called an edge case, a corner case, right? If you were to draw a box, right, and you were just, come on, there we go. And if you were to try to fill this in, I'll make it look even nice, right, with red, right? Right? You can be really, really careless when you go ahead and fill this box in as you're moving along here. You go back to grade school and you're coloring now. But when you get to the edges, right, can you be careless? When you get to the corners, can you be careless? You got to be really, really precise there, right? You got, there, I already went over the line, right? So those are edge cases or corner cases that you might have to deal with separately. And likewise, this is one of those edge cases, right? So anything else? Yes, edge case, right? If the list is empty, change the head to the new node. Right? In fact, I'm going to renumber that because I've already created the new node, right? I don't want to duplicate code, so I'll say that this is 1.5 now. Have I talked about BASIC before, the programming language BASIC? So there's this programming language called BASIC, and every line number, you numbered every line. So it was like 10, print hello, right? 20, print world, right? 30, go to 10, right? Something like that, right? Why did we go in increments of 10 way back when we were doing BASIC? Because we thought, oh, what happens when we need to add something between those two lines, right? It gave us at least 9 lines to work with. So I'd put 15 in there and print space or something like that, right? And then, of course, if you filled it up, then you're kind of screwed and you'd have to renumber every single line, right? It was a really stupid way of doing a programming language, but whatever, right? Anyway, I'm going to go ahead and use 0.5 there because I learned from BASIC that you don't want to go in increments of 10 here. 1.5. If the list is empty, so if this list is empty, right, then what I'll do is I will say this dot head is equal to the new node, and then return immediately because I'm done. I don't want to do the rest of this stuff down here. Okay? How do I determine if this list is empty or not? Size. This dot size is equal to 0. That tells me that it's empty. Oh, wait. Did we have a size? We did that when we had an array-based list, because an array of size 10, if there were only 5 elements in that, it had a capacity of 10. So we kept track of this differently. Maybe we now need to keep track of this differently. In other words, I'm going to change the interface and the implementation here because I've discovered, you know what, it's going to be really convenient to do that. Private int size. That means I need to take care of it here, is equal to 0. And also it's going to be very, very useful. In fact, I'm looking ahead down here, I have to provide a size. If I'm keeping track of that, guess what? All I need to do is return this dot size, and I'm done. So, two birds with one stone with this one way of doing it. In fact, I don't even like that. If the size is equal to 0, okay, that must mean that it's empty, right? Let's put that into a function. This dot is empty. Look at how much better that is. Now, it's not compiling, but look at how, read it. If this list is empty, right, other than the keyword list there, right, if this is empty, right, it's basically English if you put it into a function. That is way easier to read and understand. We call that grokking, right? Can you grok it? Grok, right? Can you understand it? It comes from a Heinlein book. Is it Heinlein? I think it was, right? Stranger in a Strange Land, right? Anyway, let's go ahead and put that into a function. Public Boolean is empty. In fact, that seems so fundamental. Maybe I want to promote that up to my interface and make all lists have this kind of functionality here. Right? We'll do that later though. Return this dot size is equal to 0. This is a Boolean expression. It's either true or false. It's going to end up returning true or false. If there's nothing in it, then yes, it is empty. Right? If there's something in it, then it ain't equal to 0, and therefore it is not empty. Right? Would it make sense to have something like this? Public Boolean is full? Probably not. Right? Remember, why did you want to create this list to begin with? Because you want to put arbitrarily many things into it. Right? If it's full, then you're done. Right? There are some instances in which that makes sense that we'll get to by maybe the end of the week or next week. Okay. All right, come back up here. If this is empty, then add the new node. Otherwise, do the rest of this stuff. Now, anything else? If you had 4 things in there before and you added one more, what should the size be now? 5. If we're keeping track of the size in this variable, what should we be doing? Incrementing the size. I need to do it there, in that case. I need to do it here, in that case. Repeated code, right? Let's rethink this. Put the rest of that stuff into an else condition, and if you're always going to increase the size, just put it outside so that you don't have to repeat it. And now you can return. Right. There. Anything else? Nope. All looks good to me. Until we test it. Let's make sure that it works. Done testing. Okay. Must have passed. Good to go. Now, let's go ahead and debug it. Remember that I set a breakpoint here. Always switch to the debug view here. Now I've added 42, 8, 7, and, or 2 and 7, excuse me. There's my list, right? Oh man, it'd be much better if it actually printed something. We'll come back to that here in a second. But otherwise your debugger can be used to kind of troubleshoot stuff. There's the head of the list, which is a node. It contains an element called 42. There's a next, which contains an element called 8. There's a next, which contains an element called 2. Next contains an element 7. And is there another next? No, it's null. So you can see right here that the debugger is emulating this linked list. This first node is linked to that node, linked to that node, linked to that node, linked to that node. And I've got the structure that I expect, 42, 8, 2, and 7. I don't always want to use a debugger to do this though. Right? In fact, I should be using JUnit to do this. And next week with your linked list lab, you'll be using JUnit. We give it to you as usual. But what I want to do is I want to make sure that I can print the list out so that I can verify it. Right? Maybe I want to verify it before when I put in 42, then 8, then 7, and then after that. Okay? Unfortunately, the way that it works right now, by default, that toString method is just going to simply return the name of the class along with the default memory address of the Java virtual machine. Okay? So let's come over here and make a public string toString method. okay? Because I want it to print out the contents of the list. I'm going to create a string builder. SB is equal to new string builder. Because I'm going to be concatenating stuff, appending stuff. Right? Return SB.toString. Right? I'm going to start out by appending a nice little square bracket along with a space. And I'm going to end it with a closing square bracket with a space in front of it. I'm going to make it look nice. Now what I need to do is I need to traverse the list. For each element, append it to the string builder. All right? Hey, that sounds familiar. Didn't we do that, something like that up here? We established a current node that started at the head. While the next was not equal to null, right? Then we went to the next one. All I need to do is append it as we go along. Right? Actually, right here. sb.append current node dot get element. I want to make it look nice, so I will also append a comma and a space. There we go. Let's see if that looks nice now. Ugh, not exactly as I expected. The first time that I printed out, it should have 42, but it doesn't. But the second time that I printed out, it does have 42, but it doesn't have 8. Something's going on here. Remember what we did here? As your suggestion? Did we go all the way to the end? No, we stopped right here. So that last element, whatever it is not getting appended. I could go until current node is not equal to null. But no, I actually want to stop short. Because what I want to do is I want to append the current element here. Right? So let's go ahead and run that. The reason that I wanted to do that is, do you see a trailing comma here now at all? Nope. What my intention was here is, well, if you're in the middle of the list, take the node and the element at the node and then put a comma at the end. Comma, 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 comma. Except when you're at the last element. I want to handle that separately. So with loops all the time, you're either handling the first iteration differently or the last iteration differently or something like that in order to get different behavior. If I appended that as well, then it wouldn't look as nice. Remember those edge cases though. What am I not testing with respect to the toString method right now? I tested it after I inserted something. After I inserted 2 things, after I inserted 3, 4 things. What didn't I test though? Nothing. Right? This is why you never say it's done, ship it. Right? Test, test, test. Right? What's wrong here? Right? You can't, where was it? 73? Right? What about if there's nothing in there, what is head? Null. Can you call get next on a null element? Nope. So there's one of those edge cases. If this dot is empty, man, that's coming in handy now because I can use it in multiple places. If I hadn't done that before, I should definitely, like, fire alarm should be going off in my head. That should be a huge red flag that if you've got repeated code somewhere, you should be putting that into a function. If I hadn't done that before, I certainly should be doing that now. I'll return a special string here, empty. Right. There we go. Right. That's one of those edge cases. If you didn't like the word empty, you could do something like that instead. Right. Undo. I like the word empty though. Right. Okay. All right. That looks pretty good. Next. Ooh. Add a particular element at a particular index. This is going to be a little bit different, right? Let's think about it with respect to this, this list that we had before, right? All right. Suppose that I wanted to insert at index 2. What is that going to mean? Remember that we've got indices implied here, 0, 1, 2, and 3. Right? That means that I'm going to want to insert it right here. I'm going to want to insert it in between 8 and 2, right? If I want to insert it at 2. So that I've got 42, 8, x, 2, and 7. Okay? Well, my first step is going to, of course, be creating that node, right? Once I've got that node, what do? I need to traverse not all the way to the end, but I need to traverse to that guy right there. Because what I'm going to do is I'm going to make it so that this one now points to the new one. Does that work? Nah, it doesn't do splines. There we go. I'll just do it like that. And then I want to make this one point to that one. Imagine now taking this and pulling it taut so that we have 42, 8, x, 2, and 7. Okay? But be careful. In order to make this one point to the new node, am I going to be able to do that with just current? Nope. Can I go backwards? If I get this one, can I go backwards? Not the way that I've designed this. I can only go one direction. There are things called doubly linked lists where you have both a next and a previous reference. We're not going to do that though. We'll mention that at the end. Right? Okay. So I don't necessarily need current, just need current. What else do I need? Previous. Good name for it too. Previous. Right? This one right here. And I'll highlight that one as well. So do I need to go through it once, find the previous, go through it again, find the next? That sounds kind of inefficient. What if there were 1 billion things there? And I wanted to go all the way to the end minus 10. If I did this twice, 1 billion operations to get the previous, and then another time, 1 billion operations to get the current. 2 billion operations? Is there a way that I can cut that in half? What if I just got the previous? Then could you get the next? Right there. Right? Just jump over to the next. Let's just do it once. Right? Once we've found this previous here, then we can make this point to this, and we can make that point to that after I've gotten the current. Right? So once again, let's outline this. 1, create the new node containing x. Right? 2, find the previous node at index minus 1. Remember that we're given the index here. And then 3, get the current node at index, just add index, right? Previous is next, right? Then 4, 4a, let's say. Make previous point to the new node. For b, make the new node point to the current, right? Using all those, and then what else? 5. What? Oh, sorry, I can't hear you. Oh, yeah, anything else? If you're adding something, what did we do up here? Size plus plus. This dot size plus plus. Right? I'll still leave this here because there might be some other things, right? But otherwise, return. Okay? So increase the size. I'll actually make this into 6 because I will increase the size. Increase this list's size. Right? And I just did that. That's easy. It's also easy to create a new node. Node T, new node is equal to new node of whatever containing x. All right. Find the node at index minus 1. That means I'm going to come up here and cut and paste this code again. I've already done that now twice. I wrote it here, then I cut and pasted it down here. Should I continue following that or should alarm bells be ringing off in my head saying, wait a second, why are you traversing the list every single time with new code? What if I had a function that did that for you? Public node T get node at a particular index. To do. Return null for now, just to make sure that it compiles. What if I had that? Somebody else, index minus 1. How do I get the current node? Node t current is equal to previous dot get next. It all writes itself. Make the previous dot set next, set next to the new node. It's all basically English now at this point. Make the new node dot set next to the current. Current. It was already done for me. In fact, the IDE will code complete most of it for me if I let it, right? Awesome. Now, it all boils down to this. Again, if you think, man, it would be great if I had a function that did that for me, that should be an alarm bell going off in your head saying, write that function later. Right? Now, continue writing the rest of the code as if you had that function right now. Because that's how software engineering, software development, computer science works, right? Man, I wish I had a library that serialized things to XML for me. Write the code as if you had that library, because there are libraries out there. Man, I wish I had a function that computed the square root, right? Yeah, that's built in, right? Just write your code as if you had that function. Right? And then if it doesn't have, you never have that function, then write that function, because I need that function. Right? Returns the node code node at the given index. Okay? All right. Help me out. I now actually need to write that function. I'm going to steal the code that I did up here as inspiration. Right? I'm definitely going to have a current node, but do you need to do a while loop anymore? Let's outline it over here again. If you want the node at, say, index 2, if I start at the head, go next, next. How many times did I go next? 1, 2. That sounds like a regular old for loop to me. Right? For int I equals 0, I is less than index I plus plus. All you're doing is going to the next node, next node, next node, next node. And then, of course, you need to return current node. Right? Right? I don't know if it works yet or not because we haven't tested it. Remember that feedback loop. We just implemented something. Before we go on, though, let me realize a mistake that I just made. Node t sum node is equal to list.get node at 2. Right? So I'm going to get that, that element right there that I just inserted 2. And then I'm going to do, by the way, it's integer. Right? And then I can do nefarious things with it. Sum node dot set next null. Right? What did I just do? I just did a list thing, right? I chopped off the end. Right? I was able to do that because I was able to get access to your internal workings out of this list using the node, instead of the public-facing interface. Right? This, again, is called a leaky abstraction. Right? We have leaked information about how this list is structured, about how this list is implemented by making this into a public method. No. Definitely useful, right? Up here we're going to use it, but we're going to use it in what class? In the class that it belongs to. Right? So let's make it, instead of public, make it private. Right? Now, nobody can use it outside the class, but we can still make use of it inside the class. No more leaky abstractions. Right? Okay. So where are we actually using this? Right here. Get that node, and then get the next one. All right, let's go ahead and test this. I like that I already have that list. I know that that all works. And by the way, there's a prime example of why you don't do ad hoc testing like this in practice. Because what if I go back and I break something? I would have to go back and make sure that I re-implement all those things that I just deleted. Right? List.add. Let's go ahead and go with 101 at index 2. Right? So in other words, I'm doing it like this, but instead of x being x, it'll now be 10, I said 101 or 102? 101? All right, there we go. So is it going to look like 42, 8, 101, 2, and 7? Let's find out. Run it. Ah, cool. It works. Are we done testing? No. What else should I test here? What happens when I inserted at, say, 1? It should be 42, 101, 8, etc., etc. Oh, it still works. I'm done. Nope. Do those edge cases. 0. Does that work? Yeah, 0 doesn't work. All right? What's going on there? Let's walk through it with a debugger. All right, we're about to add 101 to index 0. It should look like 101, 42, etc., etc., etc. I do not want to play. What I want to do is I want to not step over, but step into. Now I do want to step over that, step over that. There you go, step into. There we go. All right, so create that new node. Wonderful. I don't have a toString method on the node, but that's all right. There's 101. Right? So I created the new node, fine. Okay. Step over. Oh, wait, previous. Did I get the correct previous? Element is 42. There's where my problem was. Right? So let's go ahead and stop this. And now let's winnow it down to where the problem actually is. I'm going to take away that breakpoint. And I know that it's not in the integer class. I know that it's in this getNode method right here. So that's where I'm going to set my next breakpoint. Run this. Now remember that we're trying to get, we're trying to get something at index -1. Does that make any sense? Nope. So let's go ahead and stop this entire process and go back up here and realize that, when you insert something at the beginning, you end up with index 0. 0 minus 1 is -1. Can you get the element at index -1? No. Okay. So that's one of those other, we call them again, corner cases, edge cases, right? If inserting at the beginning, in other words, index is equal to 0, equals 0, then ... if index is 0, then I want to do something else, do something differently, right? Again, if I've got this list, this pre-existing list, however many things are in it, and I've got the head right here, and I want to insert this new one, is it as simple as making something point to something else? It's a little bit different in this case. Why? I need to replace the head and then make that one point to the old head. Okay? So this dot head is equal to the new node. New node. This dot, or I guess new node dot set next equal to this dot head. Careful, what did I just do? This dot head is equal to the new node dot set next is equal to the head, but the head is now what? The new node. So what did I end up doing? Head is now pointing to this, and this is pointing to the head, but the head is pointing to this. So what have I done? It's just a big circle. Okay? Swap those around, and you're good. In fact, okay, yeah, I like that. Let's go ahead and try it again. Ah, okay, now it works. So again, this is why you don't do ad hoc testing like this in practice, because now I have to go back and I have to test. Well, did I break anything when it's 1? No. Okay. Did I break anything when it's 2? No. Did I break anything when it's 3? No. Did I break anything when it's 4? No. Did I break anything when it's 5? And by the way, 5 is 5 valid? Oh, something was always broken. Right? Cannot invoke previous because it's null. Should I be allowed to do something like that? Nope. So let's go back over here to the original implementation of our array list. And let's think about how we dealt with that. Where's my array list? Where was add? Oh, I remember. We had a bunch of error checking. All right. So let's go ahead and steal that code right there. So 0, do some basic error checking. Dot, dot, dot. Right. If you give me a negative index, I'm going to throw that back at your face. If you give me an index value that exceeds the size, then I'm going to throw that back at your face. Right. Run this again. Okay. Index cannot exceed this list size. Now it works. Right. It works as expected at least. Right. Let's bump that down to 2 again. Cut. I am positive, now that we've done all this grunt work, especially this guy right here, that we can do the rest of this stuff really, really quickly. Right? Most of it, at least. What about get? Call that function. This dot get node at that index. Once you've got that node, what can you do? Get element. Once you've got that element, that's what you're returning. One line of code, because I had the forethought to design this one thing that could be used over and over and over. Careful though. What did we do with respect to get over here? Bounds checking. All right. Copy, paste over here to my linked list. Anytime you find yourself copy pasting code with no differences, again, that should be a huge red flag. What should I have done instead? I should have come over here to my inheritance hierarchy and thought a little bit more about what this should look like. This is a pure, actually, no, I can do this better. This is a pure interface up here, right? Pure abstraction. What if I put something in between, like you've done in your projects, right? Instead of a pure abstraction, I would have, say, my abstract list that implemented that thing. And then this one was a concrete list. We don't call them concrete, but a non-abstract one that did it using an array. This one is using a linked list. What could go right here that is common to both of these things? Bounds check, size, the size variable, right? Let me just go ahead and compare these two right now. Compare with each other. Right? Side by side here. Guess what? The size is shared. Setting the size to 0 in the default constructor is shared. What else is shared now? Oh, well, clear wouldn't work, but bounds check, right? Everything that is the same between these two, which is not much, but it's a little, it's enough to justify doing that. Right? I'll leave that as an exercise, though. For now, I'm just going to go ahead and steal the code, okay? Because I want to get it done. So this dot bounds check, index, there we go. We can test that over here, and we can say, for int I equals 0, I is less than list.size, I plus plus, a traditional for loop here, system.out.println of list of get I. And indeed, it has 42, 8, 101, 2, and 7, because that's what it looks like. Looks good? Right. What else could we get done in a little less than 2 seconds here? Not remove, but what about replace? If I get the element at that particular index, after I have bounds checked it, right, then I can set the element to be x. Now I still need to return the original element, so I do need to save that off. So let's actually save this node here. Node t node is equal to that, and then I can say t temp is equal to node dot get element, and then I can say node set element to x so that I can return temp. Right? I thought I could get away with like 2 or 3 lines there, but no. Right. Unless I redesign the set element that also returns the original value. Right? So for example, I could do this so that it returns t and then it does the work for me. Right? T temp is equal to this element, and then I return temp. Something like that. Right? Or, even better yet, have another function here, public t replace element. Because maybe I want both of those things. Right? So t temp is equal to this element is equal to element, and then return temp. Oh, I like that. I really like that. Why? Because what can I do over here in my linked list now? Once I've got that node, I can say replace element with x and return it. There. I can get it down to 1 line. Right. Cool. Which one is better, by the way? This one or what I originally had? Which one do you like better, I should say? This one? This one is because why it's a little bit more Englishy, right? This is called chaining. You're chaining things together. This dot, right? You're chaining all those things together. It kind of flows a little bit better, right? They both get the same job done, right? The original version where I wrote everything out myself, you could argue that that's a little bit more readable because it's a little bit more intentional, right? That I know what each line of this is doing, but this one's just as good. Let's see. How do we replace it? So list dot replace. Let's go ahead and replace that 101 with I don't know, Justin Steele. And then we'll print it out again. Did 101 get replaced? Yes, it did, with Justin Steele. Okay. The only other thing that we have to do, and I know that we have to do it because I've got this to do right here, and it's highlighted in blue over here. I do have something around here. What is this? Oh, that's a breakpoint. So let's go ahead and get rid of that breakpoint. There we go. Right. Only one thing left to do. Right. How do we remove an element at a particular index? Visually, what would it look like? It would be the opposite of this. Suppose that we had this now, instead of red, what I want it to do, it's now black, what it is. Right? What I need to do first is find it. But also I need the previous, because ultimately the previous is going to make it point to the next. So I need to find this guy, and I need to find this guy. Basically the exact same pattern as when I wanted to insert it. So let's use that as a basis. Add. I'm not going to create a new node, right? But I am going to do some bounds checking here. In fact, I've got something to do that for me, right? There we go. Do that. Right? Now I need to remove it, so I need to find it. Right? So there's the previous, and there's the current. Right? Do that. Right? So need to delete current. Right? Dot, dot, dot. So what I'm going to do is I'm going to make the previous dot set next to be current dot get next. That's it. Right? Again, what am I doing? I am making the previous node point to the current node. This is current now, and whatever it says is next. Right? That circumvents this path right here. Right? And you're, instead of going this long path right here, now you're going immediately to the next node right there. Right? Before I did that, though, I should have retained that. In fact, I did. Return current dot get element. There we go. we're removing that element there. Once again, go through the process here, right? Instead of replacing that element, let's go ahead and remove the element at index 2. That should remove 35. Let's go ahead and print it out too so that we make sure that we're getting it. Println list.remove. Remove the element at index 2, which should be 35, and then it should end up getting removed from the list. Hey, cool. Again, from the patterns that we've been following here, am I done testing? Nope. What else should I test? All right, let's remove the second element. That works. Remove the head element. Crash. All right. What was the head element? 42. So exactly like I did over there in the add, right? If we're inserting or if we're removing from the beginning, let's go ahead and treat that as a edge case. Right? If removing the head, ... Right? In other words, the index is 0, then what I'll do is I'll say this dot head is equal to something. Right? What's that something? This dot head dot next. Right. Let's see if that works now. Hey. No, it didn't work, did it? Oh, no. Maybe I should be printing it out again. There. Let's go ahead and get rid of all. No. Oh. No, I was. So we remove 35. Oh, wait a second. Am I really screwed up now? Save this. I don't know why that's happening. Oh, okay. Now I do know why it's happening, right? Once you've removed it, what should you do? Return, right? Yes, there is something else, bookkeeping basics, that I am not doing here. Oh, I should have probably saved it off, right? T temp is equal to this dot head dot get element, and then I can return temp. There we go. That should work. That 42, 8, 35, 2, and 7. Now I've removed 42. The rest of the list is intact because I'm returning. But again, follow that pattern, right? Else, I'll put all of this stuff over here into there, right? And here, I do need to make sure that I'm taking care of the size, because if I have 5 elements and I remove one, how many elements do I have left? Minus, minus. Repeat that code down here. You could look for ways to not have to repeat that code, but it's not going to look as pretty in this case. Because what you need to do is you need to save off the element that you are going to return, right? And it's going to be completely different over here, where we've got the current node that we get the element, whatever. You can consolidate this a little bit more if you think about it. That would be clever code though, right? Readable code is better than clever code. Right? So I'm going to leave it like this, okay? Let's make sure that it works still. And also let's make sure that our size is still intact. List.size. That should be 4 in the end. Come on, run. There we go. Looks like it's working to me. Right. So from idea to implementation, along with at least a little bit of rudimentary testing, right? We've now got a fully functional linked list. Right? Now in practice, you don't roll your own. Right? There is a list interface already in Java. I'll go string here. Right? List names. Right? Is equal to a new array-based list. Right? That's our array implementation. Again, we took a look at the internals of this. How is it representing stuff? It's representing stuff using an array. Right? How is our linked list implementation in Java? Linked list. How is it, and I need to import this, representing things? Let's take a look. Hey, instead of calling it head, they called it first. They are keeping track of the tail, the last element in the list, because they actually have, and they've got a node class here. What does that look like? It's got, let's go all, oh, wait, sorry, I shouldn't have done that. I should just go to node. There we go. There it is. It's got an element called item. Instead of calling it element, they called it item. They've got a reference to another node, which is the next. They've got a reference to previous as well. It's one of those, what they call a doubly linked list, right? So what you can do is you can have a node here, and I'll make it slightly larger because the element is stored right here, but then you've got a next element, and you've also got a previous element. That's a little bit more flexible because you can work one way, but then you can also work backwards. All those instances in which I said, okay, I need the previous and the current. Okay, I'll only get the previous because I know I can always get the current. Well, now you can get the current and you can work backwards and forwards. You don't have to worry about going one way just all the time. Right? There's the node. How is it represented with respect to size? Oh, hey, they keep track of size as well. Right? So basically, we gave you a basic implementation of how they do it in Java. In practice, you would never write your own linked list unless you're required to do so, like in a course, or for some reason you had a terrible language that didn't have something like this, or whatever. Right? You wouldn't write your own array-based list. You would use whatever's built into the language. But knowing when to use one versus the other, that's the key. Right? Why? Because you remember that this whole thing started, or I introduced linked lists because of that demonstration that we gave last week that I'll repeat on Thursday. On Thursday, where we wanted to clear it out. Right? My linked list. Right? Do you remember how clear worked? Public void clear. Right? It makes it empties out the list. ... How does that look in our array-based implementation? Well, my first version of that was as follows, right? While this dot size is greater than 0, I will this dot remove at 0, right? Over and over and over and over again. That will literally take weeks, right? Whereas then we thought, oh, wait a second, we could just say that the capacity is now 0. Right? Over here with a linked list based implementation, it's even simpler. Right? How could I clear out the list? What would I do to the head? Make it null. This dot size, make sure that you're changing that too. How many things are in the list now? 0. Automated garbage collection takes care of it all. Right? So we'll see with a demonstration on Thursday that even if you use the built-in linked list, even if you use the built-in array list, those limitations are there. Again, remember the quote, you can, to become a world-class programmer, you can program every day of your life for 10 years. Or you can program every day of your life for 2 years and take a data structures and algorithms course. Because knowing the difference between linked lists and array lists and how they work is the difference between when should I use that data structure over there? No, we're not going to use that data structure over there. Or we're not going to use it in the way that you want to use it because I know that this data structure is way more efficient. Right? When somebody sits there and says, why is this taking forever? I guess our computers are just slow, we need to upgrade. And you sit there and you say, well, it's because you're using a linked list, and you hit them upside the head, and you change one line of code to the array-based list, and what was taking weeks before is now instantaneous. Right? That's the difference between a boot camp programmer and computer scientists, or computer engineers, or software engineers, or whatever you want to call yourselves. Right? All right. So we'll pick it up there on Thursday with that demonstration.